Thank you, Nicola. Thank you very much for coming. Thank you very much to Christian and Laurent as tutorial chair and Christian as program chair. And as Nicola said, I'm Ian Gent from the University of St Andrews, and over there is Lars Kotov from University College Cork, and this is something we've been working on together. So I want to start off with a big statement that some of the papers at CP 2013 are really groundbreaking, in my opinion. It's these three: constraint-based approaches for balanced bike sharing, scalable approximate model counter, parametric propagator for discretely convex pairs of some constraints. Oh, wait a minute. I'll come back to that in a moment. Bin packing with linear usage costs, an application to energy management in data centers, a simple and effective decomposition for the multi-dimensional bin packing constraint, and improving WPM2 for the weighted partial max-sat. Why are these groundbreaking? Because these papers contain recomputable experiments, which means you, and I mean you, each individual in the room, if they wish, can go and download a virtual machine. You can run the experiment. There's a very simple set of instructions. In two cases, there's some issues with licenses, which we'll come back to in the second half of the talk. If you want, you can build on these experiments, you can improve them, you can check that what they said in the papers is true. If the experiments are perfect, you can learn from them. And we've been having some website trouble this morning, but fingers crossed, you can get them from Recomputationorg. So let me just, if you were in the room earlier, you saw this. And this is a little video, because I didn't trust live. But this is just a snippet of a video of a shell working on my Mac of running one of these experiments. By the way, I'm glad you're following the video, because at some point, I walk around quite a lot, I know exactly what's going to happen, and it's that. And it's going to be a great moment in CP history. So what I've done is, I've started this video halfway through the process, but here's the complete set of instructions, which if you went to the web page for this experiment, you'd see. This one is, I'm sorry, I've forgotten the names of the authors. I know the middle R is Rendell, because that's Andrea Rendell. I can't remember the G and the U, I do apologize. This is the first paper on that list. Here's what I did. This is on my machine, on my Mac, and before lunchtime, I had none of this stuff on the Mac. So I did this: make dir GRU, cd GRU. Right, this is very subtle and complicated. I made a new directory. There's a program called Vagrant, which we'll tell you briefly about. It's a wonderful tool, which is not ours. We have nothing to do with this. Vagrant init, this line of text here with the URL. Did that before, just after the lunch break started. Now, then the next line here, Vagrant up, and that is all I typed. I've just told you everything I typed to get this to run. Now, the reason I've done a clip of this is there was 20 minutes while it downloaded the experiment. So on our EduRoam here, it took me 20 minutes to download this box. I think it's something like 800 megabytes or something. But when I uploaded it, it did this, and then so the video started in the last few seconds of downloading the box. Now what it's doing is it's booting the box. It's not quite booting it, it's exporting it and installing it into VirtualBox. And this is getting a little bit boring. I was hoping I should have talked slightly slower, but I can just slightly fast forward through this video. Oh, 99%. What's going on? Where's my control? Right, so, we're nearly at the end. Let's just fast forward a little bit. There we go. So this now is booting. So all this stuff is now booting the box and waiting for the virtual machine to boot. Blah, blah, blah. This can take a few minutes. It didn't actually take a few minutes. Stuff, all these are messages. And then I'll just let that run. Do you see that just appeared? I've done nothing, right? I haven't typed anything since I typed Vagrant up a few minutes ago. This is the code produced by Andrea and her colleagues, given to us. Lars put it in this virtual box, and I know nothing about this experiment, and I can run it. And on my machine, this morning, I had no part of this experiment. It all downloaded, and it all ran automatically. And I didn't even have to read instructions to say, cd this, and build, and make, and .configure. It just ran. So I think, when you see this happening, you think, this is the way we should be able to run each other's experiments from previous years or from this year. I've got a lot of acknowledgements, and there's too many to thank. And there are many people not on this slide. I've already said thank you to Christian and Laurent. St Andrews and Cork universities have provided a lot of help with systems and machines and so on, and my time and Lars's time. John McDermott St Andrews, who's been fixing the website almost every day. And these are the authors of the papers who have contributed recomputable experiments. So thanks very much, especially to all of these guys. So this tutorial, there's two parts and an encoder. First, I'm going to talk about what I call the Recomputation Manifesto, which is a sort of big picture, pontificate. Right? Any assumption that I'm a professor and therefore I pontificate, and Lars does detailed, high-quality work, is totally, I won't finish that sentence. So then Lars will talk about how we did the recomputation, such as you've just seen, and how you could do it. Because this tutorial is partly about saying, please work with us, but it's partly saying, please do these things yourselves. Finally, we'll briefly at the end say, how can you help? Because I want to change the way we all work in constraints and in all of computer science, and so we'll ask for your help with that. What's a bit of background? Officially, everyone's learned some scientific methods. Officially, replication is the key to science. Somebody does an experiment, somebody else does it again. Unofficially, what's the situation? There was a lovely Twitter hashtag at the start of the year, which was called Overly Honest Methods, and people talked about how they really ran experiments instead of how they did it in papers. And this was my favorite. You can download our code from the URL provided. Good luck downloading the only postdoc who can get it to run. Right? So this is the problem we're trying to solve. If some amazing postdoc has done some great work, we should be able to run their experiments. So that's what we should fix. Experiments should be downloadable, and critically, they should be easy to run. The word recomputation, just by the way, I haven't made it up, it's a word older than the USA, which is lovely, 1766. But I have added a meaning, which is I mean exact replication of computational experiment. And I was a bit scared when I approached Christian about this, because there's recomputation in constraints, has specific meaning in constraint solvers, and Christian's written about that. But he didn't hit me, so that's very kind, and he was very keen on this, so I'm really, really grateful. I've written this part one, it's called the Recomputation Manifesto. This is, you can get it off archive, and I did a blog post, so if you want to read more thoughts. So let me say a few things that I'm totally unashamed about, and people sometimes argue with me, and I say, well, tough, that's the way it is. First of all, I am talking about exact reproduction or exact replication of an experiment. And often people say that's actually not scientifically the most important thing, and they are correct. Because if I've done an experiment and said algorithm X does this, and it's better than algorithm Y, you shouldn't, the fact that my experiment proves that, doesn't prove it, seems to suggest that, doesn't mean another experiment done by somebody else would. But I'm talking about, if I've done this experiment, I want you to be able to redo it. So this is sometimes called bit replication. Second one, you might consider to be a bit overambitious. I want to change the way we do computer science, so certainly constraints, because obviously I come from constraint programming. But absolutely, I think the way we do computer science is flawed because, there are many other ways it's flawed, but because we can't reproduce experiments. And so obviously I'm going to need help to do this. So please help me, and Lars. So the Recomputation Manifesto comes in 6 points. Some of them are not very controversial, a couple of them are. So the first one is computational experiments should be recomputable for all time. I've just noticed this slide has come in at the wrong point, which is, but let's do it anyway. I felt every talk has to either have an XKCD or a PhD Comics or a Dilbert cartoon. So this is from PhD Comics. And it's kind of making the same point as the overly honest methods thing. Says how indispensable you are. Wow, you're the world's expert in this topic. Oh no, you've documented your experiments and software too well. Anyone can continue where you left off. So the problem is there's a lot of people up here and there aren't enough people over here. That's what we're trying to fix. So as I say, that kind of is in the wrong place. So just a reminder, computational experiments should be recomputable for all time. Why? Often people talk about the sort of useful lifetime of an experiment. And to me, there is no finitely sensible limit of how old an experiment can get, and then you can kill it. My analogy is, imagine if we could look through Galileo's telescopes, but we hadn't bothered to keep them. Or there was a postdoc who worked out how to look through them, and then that was it. And this would be appalling. But it is appalling. I mean, this thought is horrible, and it's happened many, many, many times. And it shouldn't happen. My favorite example of this is from Schrödlu, which is one of the most famous AI programs from the 70s. And the really interesting thing about this is, so I won't tell you, if you don't know about this, you can find out, but it's a seriously famous AI program. The source code exists, which is quite surprising from the 70s, but Terry Winograd kept the source code and it eventually found its way onto the web. So you can go and download the Lisp source code. Also, you can get an emulated machine that it ran on. So you can get a copy of the machine, whatever it, some PDP or something, and the operating system that it ran on, but you can't run his code on that machine. Because what you need is his code on that machine in the state it was on the day he ran the experiment. So, for example, I believe he'd hacked the binary of the Lisp to do something slightly different. So the Lisp executable that maybe is in the virtual machine is not the one he actually ran his experiments on. So we can't run it. And there's one of the most famous AI programs in the world, and we can't run it, even though we've got the source code and we've got the machine it originally ran on. So that's the first one. The second one, recomputation of recomputable experiments should be very easy. And that's been a big focus of what we've been trying to do. And I believe, to some extent, it could always be easier, but that little video showed you what I'm talking about. There were 4 lines of text in a terminal, and I could rerun the experiment in an area I know absolutely nothing about. I've got another example here, just because it's sort of explainable, and because the experiment, unlike the real papers, this is a sort of demo experiment that anyone can go and download if they want. It's on the website, and the advantage of this one is it only takes a couple of minutes to run. So if you want to run it, it only takes a few minutes. It's a nice little puzzle. When I was doing some work with Barbara Smith and Karen Petrie some years ago, this was a side product of this on Peaceable Armies of Queens. And this is a chess position where there are 9 queens of each color, 9 white and 9 black, and none of the queens is on the same attack by any other queen of the other color. And also there's 2 kings, and the 2 kings are on the same diagonal, but otherwise they're not on the same line as any other queen, right? So, and I claim this is unique. The cute thing, the reason I particularly love this is A, it's unique, B, you can get 9 queens, right? There's a queen, and there's 8 black pawns, that's 9. There's 8 white pawns, that's 9. So you can actually get this on a chessboard. If you think about it, you don't think, can the pawns get past each other? And the answer is yes, they can. Anyway, if you wanted to do this experiment, and there's a web page on Recomputationorg where you can, if you get these instructions, here's what you have to do. You have to install a thing called VirtualBox, which is a famous virtual machine program. You install a thing called Vagrant, which is a wonderful wrap around VirtualBox. Neither of these comes from our website. You just go and get them. They're free. You open a terminal, you do make dir something, cd something, this thing here, and then you do Vagrant up. And then what will happen is, it'll take a while to download the machine. When it's downloaded, a couple of minutes later, you'll see the results confirm that. As I've said earlier, it's important, that won't confirm that my claim about this position is correct, but it will confirm that the data I ran, the experiment I ran, did what I says it does. I might have made a mistake, there might be a bug. So it might be wrong, but that's the general idea. So next point, tools and repositories can help recomputation become standard. So obviously we've got one currently very small repository at Recomputationorg. And what's happened? Thank you, Edurome. I've got a little thing saying enter my username and password. I'll just switch my wireless off after I've found the mouse. Okay, let's go back to the talk. The surprising thing is, such a great technique for getting audience members to wake up. They think you made a horrible mistake and actually it was all deliberate. Okay, so we've got this little repository. I don't want you to think we're the only people doing this. There's quite it's a space there's quite a lot of activity in. There's various things run my code. iPol, this is a particularly interesting one. So this one is a journal. Obviously it's not in my area, but it's an image processing journal. If you want to publish in that journal, you must provide your code in an executable format, and then I can go to the journal, and I believe because it's image processing, I can give it an image and see how that transform performs on that image. So that is a fantastic one. My experiments share. There are tools which are related to experiments, but we need more, and we have a particular focus. So this is a slide answering the question, why not just use one of those tools? And so there's a few answers. We want particular things. We're trying to hit a particular combination. And one of them is we're focused on experiments in computational science. Okay? So we're not about having, for example, a testing library or something. We want computational experiments, so which liberates us from certain aspects like, does the whole code base work? We only care about, does this experiment work? We want to be totally open. Anyone in the world should be able to get the entire experiment, look inside, see how it's done, see how it works, improve it. There are licensing problems with that, which again we'll come back to. This is a really important one. We're totally agnostic as to the form of your experiment, as agnostic as we can be. So, for example, you might write a library for running every algorithm on a set of instances. We're not interested in that. We're interested in having that library being able to run in a virtual machine, and then we supply you the virtual machine. A lot of the tools I just mentioned, for example, are really, really good, but they might be restricted to Python or R or some other language. And I'm interested in experiments which do have some special purpose code written in a random language with maybe a Python script at the end and an R script to do some stats, and so on and so forth. We're dedicated to being around for a long time. Whether we achieve this is another question. And when hardware changes significantly, we could have a problem running old experiments. But we haven't faced those yet because we're new. So we have this website, Recomputationorg, and the idea is if we can compute an experiment now, anyone can recompute it 20 years from now, hopefully forever, but no guarantees. And as I've just said, we want to take free-form computational experiments, provide VMs, and keep experiments around. This one is one of the most important, if I had to have one of these slides, it'd probably be this one. It should be easier to make your experiments recomputable than not to make them recomputable. Now, this starts off being a bit paradoxical, because this is a bit like a general purpose method being better than a special purpose one. You can always pretend that the general purpose one is special, so you can never actually be better, because there's always one more step to make it recomputable than not to. So it could be paradoxical. Maybe I haven't expressed it very well. But there's a guy called John Claerbout. I'm not sure how you pronounce it, but I'm saying Claerbout. And he said, it's not really for the benefit of other people. Experience shows the principal beneficiary of reproducible research is you, the author yourself. And this reminds me of way back in about 95, the web was coming, and somebody said to me, why should I bother to have a web page? What's in it for me? And I said, since I made a web page, I have been able to find copies of my own papers. Right? And it's like this. You should be able to do your experiments again, easily. And if you can, it's easier to do the next experiment, and the next one, and the next one. So your whole life cycle will be easier and better if you make your experiments recomputable. I've often had problems running experiments I've run in the past. And when I say problems, I mean it has been impossible for me to do it. And I've had arguments with editors to say, they said, well, could you just rerun it with, delta equals 4? And I've said, no, I couldn't. And that shouldn't be acceptable. So it should be easy to rerun an old experiment. And then if that's easy, it should be easy to hack it to be better. I've got a couple of, the next couple of points are the ones which often cause controversy. So I'll just flag that up. But I'm pretty convinced this is the way to go. The only way to ensure recomputability is to provide virtual machines. Now, the reason for that is that there could be arbitrary aspects of your code that mean it doesn't work on my machine. So we really need to have a virtual machine that it runs in. But it does raise a lot of problems, bandwidth, storage. You might think it's overkill. I've got one, take that Queen's example, it's one G-code file, it's a few K, and yet I'm giving you hundreds of megabytes. So you could say that's overkill. Long-term persistence, because maybe VirtualBox will disappear. But I just don't think there's an alternative. And the Schroedler example is one of the things that convinces me of that, because we've got a virtual machine, it's just not the right one. And nobody's been able to run it. My key response is, and this is actually really important, if you want to give me an experiment, you shouldn't have to upload a VM to me. And this is one of the things that scares people. I've got this experiment, I've got to give you a 30 gigabyte VM. And the answer is no. I believe, I'm looking at Lars, nobody gave us a VM, did they? No, so we've got these 6 experiments, people gave us directories, tar files, what have you. Nobody gave us a VM. You don't necessarily have to download them. So we haven't done this for the current set of experiments, but in principle we can give you other things like tar files that will work if you've got the right environment. So the point is that virtual machines almost dominates any other method, because sometimes people say, there's this lovely thing I can use. There's a thing called Docker, for example, which is a sort of lightweight thing. But if that works, we can steal that idea, put it in a virtual machine, and now we've got a virtual machine that works anyway. So we can still provide the virtual machine. So in a way, there may be other things which are really great, but they don't stop us doing the virtual machine. And the more ways of recomputing experiments, the better. So the last thing I want to think is anyone to go away and say, that Ian and Lars, I've got to hassle virtual machine, blah, blah, blah. No. If you've got a great way of doing your experiments recomputable, that is fantastic. And hopefully we can work together and put those in virtual machines and so on to make it even easier. Here's one which again I think is even more likely to be controversial in this audience, which is runtime performance is secondary. So one of the very first things that most people in a constraints type environment would say is, I've proved that, you know, my STR algorithm, whatever it is better than his GAC table. And I proved it because it ran faster. So how dare you say that runtime performance is secondary? That's a very common response. And it's often true, I don't want to minimize the importance of this, it is often true that runtime performance is the key issue that you care about as a scientist. What you really care about is, Peter Stuckey said this in his invited talk. He said, I don't care whether something's GAC or domain consistent, right? I care about number of explanations generated per second or number of propagations made per second, right? So, yes, that's true. So this sometimes puts people off, and just in case, sorry, I've kind of taken it as obvious, the point is in a virtual machine you may get very different runtimes to the real machine you run it on, okay? And then you run it on the same VM on different hardware may run in different times. Sorry, I should have maybe said that. Here's my response. There's two aspects to it. One, if I can't recompute it, if nobody can recompute it, there's no way we can reproduce the runtimes. So this is a sort of stupid answer, but it's like, you know, yes, if you don't like what I'm doing, at least make it recomputable and then improve it for the runtimes. But I think the better response, and the more I think about it, the more I'm convinced of this, is that if I get very different runtimes, so for the sake of argument, STR algorithm A is better on your machine than GAC table algorithm B on your machine, and then in a virtual machine that swaps around, for example, that is extremely interesting information, which is of scientific value, and it's not something to be hidden and brushed under the carpet. So if we get runtimes which are different in different environments, that adds to our understanding of whatever it is this experiment is about. It's important, it's interesting, and we might bring these things to light. Because if I've written this paper with short STR in it and some GAC thing, whatever, and I put them in the machine, you can rerun them and say, oh, I got different results to you. I wonder why that is. And that can be really interesting and important. There's some conceptual challenges. So a lot of the work we have to do is technological, building virtual machines, scaling, cloud, and so on. But there are some really interesting, I think, conceptual challenges. So one of them is, what is an experiment? And that isn't always obvious. So, for example, does a paper have one experiment in it, multiple experiments? What is the history? You may have, what is the identity of an experiment? When is one experiment the same as another one? Okay, this can get a bit philosophical, but you know, I've run this experiment on my machine, then you've run it on yours, but then you've upgraded your operating system. Is that still the same experiment? And you make incremental changes. What does it mean to be a recomputation? This one, the third one, how do we know an experiment is recomputable, is one of the biggest challenges Lars and I have faced, and in some sense we've given up, and we don't have an answer to this. Some of these, Lars will tell you about one experiment where you need 1.5 years CPU time to run it, and we haven't had that amount of time. So how do we know if we've made that experiment recomputable or not? Because even if we ran it, how do we know it's recomputable? What if we get a different result to you? You're giving me an experiment, I run it, and I say, no, the answer is 8, not 7. How do we know whether I recomputed it and there's some variance, or there's some bug in the virtual machine or something? Another really important one is partial recomputation of an experiment, which again is not obvious. That's fine if I've got a paper with 3 things in it, and I do one, and then I do the second, and then I do the third. It's not obvious in general if we've got partial points. So I'm winding up on my part of the talk. We'll move on in a few minutes to the more, what I like to call interesting part of the talk from Lars. One thing when I say I want to change the way people do science, I don't mean it in a boring stamp collecting way of, you submitted a paper, therefore there's the experiment there. And that's not actually the whole story. Yes, it's really, really important. The replication of scientific experiments is critical, but there's so much more than that going on. We should be able to do better science, and I believe we would all do better science. Anyone who does experiments would do better science if they were making their experiments recomputable in the loose sense. I don't necessarily mean submitting to our repository, but in the more general sense. Imagine if you're trying to program without source code control, without testing, without libraries, without code reuse, without IDEs. That's what we tend to be doing when we're doing experiments. So if I was trying to sell you source code control, and so imagine I'm trying to say, there's this amazing thing, it's going to be called source code control. And I say, it's brilliant, because you can go back in time a year to how your code was exactly 12 months ago. And everyone would go, that's so boring, that's so unimportant. But source code control is something you can't live without. Testing, same thing. Well, I found a bug. It's like, big deal, people find bugs. Testing should be in your entire life cycle. Source code control, we write papers with source code control. You write single-authored code with source code control. It's absolutely essential. Just like Git or Mercurial or your favorite source code system isn't about going back in time. It's about recovering from disasters. It's about collaborating better. There's so much more to it than just the sort of snapshot motherhood and apple pie stuff. This should be something that lives throughout our experimental life cycle. So this again is a point I sometimes can give the impression that I want you to do your experiments, get to the end, when your paper is accepted, produce the recomputation experiment. And that's not what I want. I want you to be doing it the whole way through, and then you just give me the snapshot. So Lars said yesterday or 2 days ago, he said, once you have it, I'm not sure if he, okay. What he said was, once you have it, you can't imagine how you live without it. And that's what I want you to think in a year's time or in 5 years' time. How did we do science when we weren't making our experiments recomputable? Okay, so that's my sort of half. Lars will get himself, flipped around. So, it's probably a couple of minutes for questions if anyone's got any. Helmut. Yeah, that's a very good question. Just in case you didn't hear it, does my idea of recomputation include running the algorithm with different data? And the answer is a definite yes and no. In the strict sense, you've submitted a paper and it's got this particular data, so there's a sort of strict, boring sense of no, because that would just mean, but absolutely yes, we should be able to do that. So it's not the sort of current number one focus, but absolutely you should be able to do it, at least in principle. And the only thing I would say positively, although I've sort of said no right now maybe, the positive thing is that, you can go and get the VM, and if you can figure out how to do it, you can change the data in the VM. But indeed it would be better if we could pipeline the data in, and so on. Christian.
One question I have, so when you do experiments, you create a lot of data, but then typically when you write a paper, you write some scripts, hopefully, that turns the data into, some human readable form, tables, graphs, whatnot. So how do you deal with that? Right, so because running the experiments is one part, running the part that actually interprets the data, right, is another one.
Yeah, so you're right. We've got an example where at the minute the approach we took, at least for CP, is we didn't do anything like that, but And one of the authors did do that. So they provide the script which generates the figures. So there's one thing where Lars will show you, we do get the figures, but at the minute we worked on the basis of, the data was the output. Indeed, the figures are often the output, but maybe the authors do a lot of work manually to get that, and we weren't trying to capture that. Yeah, there's somebody, yeah.
I have just a very simple question, and if you addressed this already, then apologies. How do you deal with scale-out computation? So I've got a program that runs on 10,000 cores.
That's a big problem, and I haven't addressed it, so there's nothing to apologize. No, that is a real problem. So, I mean, we haven't tried this, but scaling to sort of 4 and 8 cores, things like Vagrant and VirtualBox can deal with that quite easily in principle. But indeed, you've got a weather model, you predicted the weather, and you want to say, we can capture the VMs, we can say this is what happened, but it goes back to the question, how do we know it's recomputable? So the answer is I don't have an answer to that. I mean, obviously, if you've got enough, there is one answer which is actually, I believe, isn't facetious, it sounds facetious. If you wait long enough, it'll be free, right? So the same question 20 years ago, you say, in 20 years, I will come into a building and I'll take my phone out of my pocket and I'll run your experiment as my boot screen. And you would fall about laughing, and it would be completely true. So that is a slightly facetious answer, but it's not really. If we can capture the experiment, then maybe if you wait long enough, actually there will be the resources out there to do it. Yeah?
One question, in the case of randomized algorithm, you may want to reproduce the mean behavior of the variance or higher order moments, or you may want to fix the seed, hopefully making the algorithm deterministic, but it is not so clear it can be achieved that way. And so, can you comment on it in that case?
Yeah, I mean, you could have an extreme case where maybe your machine has a hardware noise random generator in it. That would be an extreme. Actually, that would be more of a problem for us. If it's the case of the seed, yes, it would partly depend on this kind of comes back to one of those conceptual challenges. What does it mean to be recomputable? So you've got a random thing. Let's say you haven't, if you've stored the seed, it's deterministic. Ideally, we would get the same answer at the end, right? But if you haven't stored the seed, or there's some variation in the floating point arithmetic or something, then hopefully you would get results that were consistent, okay? And it is perfectly possible that the results might look completely different. If I run it, you ran it, and you solved 100% of the instances, and I solved 95%. And that might be just because of different random numbers. So to me, that would be a success, and like the runtime thing, it would tell us more about distribution of results. But it might make it really difficult to know whether or not you've really captured the exact computation. Okay.
How would you deal with sensitive data? I mean, the industry gives you data, and you can't make it public, but you still want to make the experiment recomputable.
Yeah, so how do you deal with sensitive or private data in some sense? It's quite similar to the issue of dealing with licensed code. And I think there's 3 levels of answer. The best answer is make it public anyway. Make your code open source, right? And there's a thing called the Science Code Manifesto, for example, which is all about that. However, if that's not possible for whatever reason, the next one is, and this is what we did in this case, is we were able to get the access to the code through our licenses, and therefore we can run the experiments, but we can't give you the experiment. So we can give you all the experiments, and again, you will see this. We can give you the experiment with a bit missing, and if you can supply that bit, then you can rerun it. So that's the sort of middle one. So maybe this is how we ran the data, the experiment, but you've got to provide the data. And the third one is, even if it's all completely private, you can still make your thing recomputable for your lab, your colleagues, and so you can still get the benefits in terms of reuse and all of that, even if nobody else is allowed to see it. Okay, so I think we should go on now with Lars.
Okay.
So it'll be a great pleasure for everyone for me to shut up. So thank you.
Okay, is this on? Hello? Hello? Yes? Okay, excellent. So I'm going to talk about the part that is a little bit more level, and in particular I'm going to tell you what we actually did for the CP and how we made certain experiments recomputable, and then I'll again go into a little bit of detail as to what you would need to do if you wanted to do the same thing. And hopefully by the end of this tutorial we'll have you convinced that A, this is a good thing to do and you should be doing it, and B, that it's relatively easy and not as painful as you think it might be. So Ian talked more about the general idea, and this is something we have developed in the last half year approximately. As far as the actual implementation of these ideas go, we are not quite as far along. So all of this is very preliminary stuff. I'm going to talk about what we did specifically. So don't assume that this is how it's going to stay, or even that this is the best way of doing it. This is just this was the easiest way for us to do it, given the time available, and what we currently have. And yeah, so that's also why I have this second title slide, when theory meets practice, because, well, on one hand we have this grand idea of making experiments and everything recomputable, and then on the other side we have practical constraints such as, well, how do we actually tell whether it's recomputable, what Ian briefly talked about earlier, which make these things quite hard to do in practice. And then there are other issues that you thought might be a problem, but that turned out that they weren't. And I'll go into a little bit more detail on that. So here at CP 2013, we've done this for the first time. Thanks to Christian Schulte, we were able to send out email to all the authors of accepted papers, in an email that many of you probably saw, asking for participation in our Recomputation initiative. We've had 11 expressions of interest, so people replied, said, yeah, this is great, I want to participate, what do I do? And of these 11, we have turned 6 into recomputable experiments that you can run and download at home or on your laptop or at work or wherever so far. The kind of 1.5 live systems available. So there's the main website at Recomputationorg, but also specifically for this tutorial we have set up a live system that you can use to actually rerun the experiments and see the results for specific runs, and I will demo that later unless I happen to run out of time. Okay, so this is essentially how it worked. You send us your stuff and we make it recomputable. So at the moment it is a completely manual process. You send us something, you send us all the things that you think are important to rerun your experiments, such as your instance files, your binaries, your information about environments, etc., etc. And then we go away, we set up a virtual machine, we put all the stuff in there, we see, well, does it actually run? Oh no, I need to compile that. Oh no, I need to install this library here. And then we run it, and we get a list of results. And we send those results back to you and say, does this look like it's reasonable? And you say, well, okay, your machine is a bit faster, but apart from that, it looks fine. And we say, yeah, it's recomputable. So this is what we did. The general approach, as Ian already talked about, we have used 2 key technologies here. One is VirtualBox, which is a virtualization software, and the other one is Vagrant, and that is a sort of high-level abstraction layer for virtualization. And in particular, with Vagrant, you're not tied to VirtualBox. So even if VirtualBox went away because it's now owned by Oracle, and Oracle might decide, oh, actually, we're not going to give you that anymore. We could use VMware, which, okay, is a proprietary software, and the main reason why we haven't used it for our current set of experiments, but at least there's a choice. And it's not the case that if VirtualBox goes away, we are stuck and we have to redo everything from scratch. Vagrant also allows you to package up the virtual machines and distribute them. So you run a single command on your command line. It takes the virtual machine, it takes a snapshot of its current state, puts it all into a file that contains the disk image, metadata, and everything else you need to basically re-instantiate the virtual machine. You can then move that to another computer. You can import it, again, using Vagrant, and it will set up the virtual machine in exactly the same way it was when you exported it on that other machine, which is obviously very important for us because that's the whole idea. So we make it recomputable, or somebody else makes it recomputable, and then you can go and download it and run it on your machine. Two specific, not modifications, but two specific conventions that we have adopted for these experiments are that the experiments will be run automatically when you start the virtual machine. So there is no need to interact with the virtual machine after it has started. You don't need to SSH in and then run the script here and run the script there. You just start the virtual machine. It automatically runs the experiments, and once the experiments are finished, the command returns and you can shut the machine down. And the results are available in a shared folder on the file system of the host. So again, even if you want to get the, well, you probably do want to get the results when you recompute the experiments, but you don't need to go into the virtual machine and find out, oh, there's a file, it's written there, I need to copy that, and then maybe I also need that. All of this is taken care of. It's copied into a folder on the host file system. So you shut the virtual machine down, then you go into that folder and you can have a look at what's there and what the results look like. Challenges. What were the hoops we had to jump through to get all this to work? So we basically needed to replicate the environment the experiments were run in for all of the experiments. And this includes things like the operating system, the specific library, sometimes even the specific library versions. The problem with this is that it's usually not specified. So if you take a look at a random paper in the proceedings, you probably won't find information that is detailed enough to replicate the environment. So the authors might say, oh, we ran this on Linux, or even we ran this on Linux, on this specific version of Linux and this specific distribution, but they're not going to list all the libraries that you need with their specific versions. So this was a bit of a challenge because somebody would send you, the authors send us some scripts that they used to run the experiments, and then you put it into a virtual machine and you run it and it says some error, and then you have to figure out, oh, okay, this particular library is missing in this particular version, install that, try again, different error, install that, repeat. But it turned out that in practice, this was actually surprisingly painless. At least for me, it was surprisingly painless. Because it was usually after 2-3 iterations of running the thing and installing the library, it worked. So I thought that this would be more of a problem in practice because some people are certainly very specialized subs and very specialized environments with specific versions and specific libraries that you can't get in public software repositories, but this was not the case for the experiments that we prepared. So everything there was relatively smooth. As I just said, experiments may rely on specific versions of software. So you can only repeat the experiment with this version. With every other version, it will crash because it relies on some weird bug that was fixed in other versions or something like that. And this was actually the case for one of the experiments that we got here at CP 2013. And the library version that the author has used is not available anymore, which makes a great case for what we're trying to do, because this is today, so not quite today, but it was a couple of months ago. And if even nowadays, you can't rely on the things being there anymore because the author decided to delete that old version of the library from his website and you simply can't get it, then this is really quite a bad situation, because I would have thought that today, when you can just buy a 1 terabyte hard disk for a couple of euros, keeping around an old version of a library that is 100K is not really a problem. But not everybody does it, and if you rely on specific software, especially scientific software, then old versions may not be available anymore. As I've briefly alluded to before, the level of detail you have in a paper is usually not enough to replicate the experiments. And this is not only with respect to specific versions of libraries and operating systems, but even such trivial things as parameters for binaries. So if somebody, to repeat their experiments, just sends me the binaries and the instances, this is usually not enough because you need to give the binaries some parameters, some random seeds or whatever, maybe even just a flag to tell it what file to read. But if I don't know that, and this is some software you have written yourself that is not documented, then it's very hard to figure out how to get it working. So we needed to elicit this information from sometimes very busy authors, and this is the main reason why we've had 11 expressions of interest but only ended up with 6 recomputable experiments, because sometimes it is quite a bit of work to get it to work in an environment that is not yours. And there were, for several of these experiments, there were email exchanges going on over weeks sometimes, going back and forth, asking, okay, I've run this, but how did you run that? I can't quite reproduce the results in the paper. Why is this? Etc., etc. So this was actually the biggest problem that we had in preparing these virtual machines. So just to get all the information, because you run something on your laptop, for example. You've had that laptop for years. Over the years, you've installed 100 bits of software, and you really can't remember what all of them are or what the specific versions are. And you don't need to. But of course, if you want to run the code on a different machine, then you do need to. And this is where we come in, because once you have packaged it up in a virtual machine, you can just build on that virtual machine. Other challenges include licenses. Ian already talked about this as well. In particular, one of the experiments that we've prepared used IBM Cplex for some of the experiments. Okay, there's a free academic license, but we are not allowed to redistribute it. In particular, we can't put it up on a website for anybody to download. So we would need to check, well, okay, do you actually have a license? Are you in academia or something like that? And for now, we have decided that we're just going to avoid these issues completely by only including software that we are allowed to redistribute. And usually this would be open source software. This doesn't mean that you can't rerun the experiments and recompute the experiments that use Cplex, for example, because of this mechanism that Vagrant gives you of having access to a folder on the host file system. So what we did for this particular case is to tell the experiment to search for the Cplex libraries in that shared folder. And what you need to do as a user, if you want to rerun these experiments, is download the virtual machine, and then in the same directory that you put the downloaded file into, you put the shared libraries for Cplex. And they will be picked up automatically, the experiments will run, and there are no licensing issues because these are never distributed. And for you, it's not that much more work because you only need to copy the libraries from a place on your computer, wherever they're installed, to that particular directory. Another experiment that we prepared uses a couple of MaxSat solvers, and the authors of the paper didn't have the permission to redistribute those. And again, we chose the same solution in this case. So instead of including them in the virtual machine and potentially running foul of licensing issues and getting into all sorts of trouble, we just said, well, these are going to be in the shared folder, and at the start, the virtual machine will check what is there in the shared folder, get all the solvers, and run all the solvers that I have on all the instances. Other challenges. I give you this quote from an email I got, and I'll give you some time to read it, which is what Ian mentioned earlier. So yes, how do you deal with something like that? Because this is obviously something very big and bigger than most experiments that most people would run. But what do you do with that? How do you even determine whether this is recomputable? Because obviously a large number of resources is required. And even if you have access to that amount of resources, you probably can't dedicate them for the required amount of time to recomputing somebody else's experiment and then at the end saying, oh, I forgot a semicolon there and I need to rerun everything or something like that. So this was definitely a challenge. Other resource-related challenges were that the experiments may require a specific type of CPU or a specific number of cores, because you implemented your parallel solver and you obviously wouldn't want to compare your parallel solver to a single-threaded solver on just one core, because then you can't show the benefits of parallelism. And you might require a specific amount of memory as well. So, for example, here in the previous slide, the memory limit of 3.9 gigabytes. So in the virtual machine that we run it in, we need to have at least that amount of memory, because otherwise, well, we didn't replicate the environment. And if we don't get the same results, then we don't need to. We need to fix this to get them. But of course, we cannot guarantee this, because this really comes down to you who will recompute the experiments. So if you download the box, and the box says, I need 16 gigs of memory, but the machine that you run it on only has 8 gigs of memory, then there's nothing really we can do as people who make it recomputable, other than, well, maybe we could say, okay, you can't recompute this because you don't meet the hardware requirements. But this is something where the whole virtual machine abstraction is a bit leaky, because you still need the appropriate hardware to run this. And of course, the results you may get, in particular timing results, may be different. This is something that we have observed in practice as well, but in none of those cases it was actually a problem. So in several cases, I've sent emails back to the author saying, well, okay, I've run this with everything you've told me, I'm getting these results, and these are different from what you have told me the results should look like. And usually they said, oh yeah, this is fine, your machine is a bit faster, but it all works fine, and these are still the numbers that we would expect. So again, even though we expected that in practice this might be a big issue, it hasn't been, at least not for the experiments, for the particular experiments that we have made recomputable. So I guess something interesting to do, if anybody from Australia is here, would be to make the Minising challenge recomputable, because that's certainly something that intrinsically relies on timings. And if it turns out that in a virtual machine or on a different physical machine, one solver beats the other, and a different scenario is the other way around, that would certainly be interesting. So if any of you guys are interested in making this recomputable, come and talk to us. Just a very quick run through what you need to do to make it recomputable. So I'm assuming here that you have VirtualBox and Vagrant installed, and how you do that depends on what operating system you run, but usually it's very easy. So you download something, or you go to your package repository if you're running a Ubuntu or a similar Linux distribution, and just install it from there. So this first line here downloads already set up Ubuntu box from the distribution thing that Vagrant have set up, with a couple of virtual machine images for you to start with. And we call this my experiment here. Then you type Vagrant up. This starts the virtual machine. Then you type Vagrant SSH. This will SSH into the machine, so you get a shell inside the virtual machine, and you can do whatever you want, basically. Then you set up your experiments, and this will usually involve copying some files across and maybe installing some libraries. Then you stop the virtual machine using Vagrant halt, and finally you run Vagrant package, and you tell it in what file to save it. And that's really all you need. So apart from the actual steps that you need to set up your experiments, you need 1, 2, 3, 4, 5 commands. And none of these are particularly complex, so there should be something that you can do yourself at home, or right now, if you're bored, quite easily. The extended version of this, and this is what we did for the experiments, is slightly more complicated, because, as I said before, we set it up so it's run, all the experiments are run automatically. And what this requires is basically, just for simplicity, a top-level script in the virtual machine. We've called this recompute.sh, but there's no reason to call it that. You can call it anything you like, really. And then a bit in the configuration for Vagrant for the virtual machine to tell it that as soon as you start the virtual machine, run this script. And this is, in Vagrant, this is called provisioning, because so the idea there is basically that you have a standard image, and you have a set of different provisioning scripts that would make them into a web server, a database server, and a, I don't know, some kind of other server. And we are slightly abusing this for running the experiments. Okay, and then when you package it, you need to tell it to package that file up as well. But okay, it's not much more complicated. You have a couple of additional commands, and you need to give a couple of additional arguments to some things, but it makes it much easier for the person who wants to recompute the experiment, because all they need to do is start the virtual machine. Okay, and this is where I'm going to go to the live demo of the system I mentioned earlier. Yeah, so here we go. This is, can everybody see this? Is this too small? I can try to make it bigger. Oh, no. How's that? Better? Okay, so this is our list of experiments for CP 2013. Okay, the names are slightly cryptic. If you click on one of them, what you will get is, okay, it's loading, sending a request. This worked earlier. Okay, while it's sending its request, I'm going to go back to the slides and instead show you the screenshot I took earlier, in case something like this happened. So what you would see is, okay, it's a bit hard to read. What you would see here are the archived artifacts from a previous run. So this is a recomputation run, and all the results, as I said before, are put into a folder on the host file system, and this is what's archived here. So for every run of the experiment, you can go back and you can have a look at, well, this is the output for this particular part of the experiment. This is the output for this other part of the experiment. Let's see if that web page is loaded. No, it hasn't. Yeah. Okay, I will use the screenshots then. The only other thing I really want you to show is this bit here, which is the setup for the job. So this is the list of commands that we need to run to actually recompute this. And as you probably can't see, but the slides will be available later. And this website is also publicly accessible, so you should be able to go there and have a look at this yourself. Is that you really only, well, okay, you can sort of see this. So there's 3 blocks, here, here, and here. And in each of these, there's essentially one command. The first one just cleans up the results from the previous run. Because these are stored on the host operating system, every time we rerun the experiments, it generates a new folder and puts in additional experiments. And just for the sake of not cluttering the file system and the archived artifacts, we're cleaning that up here. The second one starts the virtual machine with vagrant up. And the third one stops the virtual machine with vagrant halt. And that's all there is to it. Okay, so yes, archived artifacts there. This website, as I said, is live at the URL that you saw at the beginning of the talk. If you have any questions about this, come and talk to either Ian or me. So, in summary, and oh yes, we'll have some time for questions. In summary, we have found that we can make experiments recomputable with quite some reasonable effort. And I say this was reasonable despite saying that there were email exchanges going over weeks with some of the authors, because this was really the first time we have done this. So before we started doing this, we had no idea how this would work in practice. And we had all sorts of potential issues, like the runtimes that we've mentioned, or even getting the environment inside a virtual machine set up in terms of installing all the libraries, all the other software that you need, which are not to be so much of a problem. And then other issues like eliciting from the authors how exactly they run particular experiments and with what command line parameters they used, etc., etc., turned out to be a bit more of an issue than we thought it would be. But of course, if it's you who makes your own experiments recomputable, then that's not really an issue, because you know what commands you run, and if you get an error message in your virtual environment, you know exactly why that is and what software you need to install to make it work. And there are some caveats and pitfalls, in particular with respect to licensing issues. What we also really haven't addressed in this is what Christian asked earlier. So the analysis of the results. We thought just having the experiments themselves recomputable so that you get the raw results would already be a step forward. So this is what we have concentrated on here. For one of the experiments, the authors were very helpful, and they actually provided us with a script that reads the raw results and then produces the figures that they have in the paper. So for one of these experiments we have this, for the others we don't. And of course this would be the next step to not only make the experiments themselves recomputable, but in particular if you have a look at the paper and you want to either verify the results or you want to compare your own approach, then it's important to know how the raw results were actually evaluated. And of course, often this is far from obvious, because you might get columns and columns of numbers, and then you might decide, oh, I'm going to pick these particular numbers here and plot them. And yes, this is not always obvious, and this is certainly one of the next steps that we want to take. Okay, so here's our motivational poster, because we believe that together we can make it recomputable, and we would like you to join us and help us in these efforts. So last slide, help wanted. Here are some particular ways in which you can help us. And these are just some of the ways, so if you think you can help with anything else, please let us know. First of all, talk to us. Tell us what you think about this. Tell us if you think that we're taking the right approach. Maybe you think that virtual machines is completely not the way to go because of X. Then we would certainly want to know that. Volunteer your experiments. I think we've had a great response from the CP audience and the authors of accepted CP papers this year, but obviously this is only a very small start, because for this to really take off, we don't need 6 experiments, we need a couple of dozen, a couple of hundreds, a couple of thousands, etc., etc. You can also volunteer your computational resources. In particular, we have a virtual machine and an experiment that would take about 1.5 years of CPU time to run. So if you have a computer that you're not using, won't be using for the next 1.5 years, then come and talk to us. You can also help us to prepare these experiments. As I said, at the moment, this is a completely manual process, and we would quite like to have at least 2 different people, ideally from 2 different groups involved, because we would like somebody who hasn't done the experiment to sort of check that it actually runs what that person expects of the experiment. Because so if you're the experimenter and you run it, and you maybe see the first couple of lines of results floating by and say, oh yeah, okay, that's fine, looks like it's working, but it might get stuck somewhere later on. So we sort of want to have a couple of people have a look at that and verify that it is actually recomputable for some suitable definition of recomputable. We are also going to need to help automate this process, because, okay, if you have 11 expressions of interest and you end up with 6 experiments, then 2 people can do that manually. Not quite easily, but it's certainly okay. If we were going to do this at a big conference and we got 100 expressions of interest, then there's no way we could do it. Even if we worked day and night on nothing else, there wouldn't be enough time to prepare this. So we certainly need to automate the whole process of people submitting experiments and these then becoming recomputable and available somewhere along with some meta information. And of course, we also want you to help us spread the word, because if nobody knows about this, then people are not going to make their experiments recomputable. But if they do, then there's just a chance that they might. And I'll leave you with our motivational poster. Any questions? Yes.
You you may want to also put up the energy cost of rerunning these things. So if I see a computer running for a year, there is a certain sustainability question there as well.
Yes, absolutely. But on the other hand, we could use that energy to heat the building. So we could have a dedicated recomputation building that is only heated by computers.
Some languages run their own virtual machine, Java more specifically. Would you say that code that is written in Java tends itself more towards reproducibility, or are you not interested in anything in that level?
So we did have some Java experiments. I wouldn't say that Java, because it already runs in a virtual machine, is intrinsically more suitable for this kind of thing, because it's really more about the environment. So you might need a specific version of Java. You might need some third-party libraries to run your code, and you will almost certainly need some input data files. And these are usually the issues. So even if you have some code that doesn't run in a virtual machine, like C or C++, if you just make the source available, nowadays it's relatively likely that you will be able to compile that code. Okay, you might have to figure out which libraries you need, etc., but there's a good chance that you'll get it to work. But of course, as I said, getting the binaries to run is really only, I would say it's less than half the battle, because you need to know how exactly they will run on what and what the environment looked like. Any more questions? I'm sure Ian would be happy to answer some more questions as well.
Thank you, Ian. Thank you, Lars, for spending your effort for such a project for the community. But I would like to ask a question which is kind of philosophical. Why do we want to recompute? Okay, is recomputation the key? Because for science, I suppose it should be reproduction, not in the biological sense, but reproducing the result, using so that I will be able to set up the environment to reproduce the result. And then the next step is to really to forecast, so that I will be able to run your implementation on different data, so that I could predict, according to the result in your paper, whether it's working the way it is. Why do I want to recompute? Because when I look at a paper, I either believe in your results or I don't. You guys can act as maybe a certification agent, saying that, oh, these guys did not lie. But after that, why would I want to recompute? So I'm just wondering whether recomputation is the key, or you should say reproduction and forecast is .org. You know what I'm asking.
So my short answer to that would be that in order to be able to use somebody else's experiments to build your own, you first need to be able to reproduce them. So if you just take somebody's code and you run it and you compare your own approach to it, you also have to be sure that you really replicated their approach and their code is running correctly. So I would see this as a prerequisite for what you have said. But I'm sure Ian has a more philosophical answer.
I think, is that being rude? That's a really good question, thank you. It's you know, I don't want to get too philosophical. I think one of my answers would be that we are, you know, we're now quite a long-lived community. They're talking about the 20th CP and so on. I think it'd be fantastic if you could go back to the CP. So part of my answer, okay, all right, I've taken a few seconds now, I can be philosophical, let me stand up. It's art. Wouldn't it be wonderful? You go back and look at what, you know, Haralick and Elliott did, or whoever, and just see exactly what they did. So it's artistically elegant. But that's actually not the real answer. That's the sort of philosophical one. The real answer to me is, you get code which just sort of gets disappeared, because it doesn't get into modern things. And it's maybe gone by the wayside. If that was available in an old machine, maybe 10 years ago, maybe 20 years ago, now there might be problems, but on a good day, say you've got some code and it's just written in C and there's not any major fancy new stuff in it, I mean there's some fancy new research, you can go back to the thing 20 years ago, maybe run your code in that old VM, if that's possible, and then say, right, mine is faster than theirs. Because nowadays, we compare I run something, and I say, well, the last person to write this about this did it on a SunSpark 5 in 1987, and it took 1 hour. What does that mean? If I could run it now, I could find out there might be some virtualization overhead, so it may not be totally straightforward, but you would actually have the ability to go back and really compare. And if you're really lucky, you might be able to either run their code in your machine by porting it, or put your stuff in theirs if there wasn't too many dependencies.
I agree with you wholeheartedly, because that's not the impression I got when you first, at the beginning of your talk. But in that case, again, the question is the key recomputation? Apparently what you're providing is an archival service for the source code, for the operating system, the execution environment, so that 20 years later, we will be able to play around with the code, experiment with it, maybe make small modification to understand the behavior of the code, but that's not recomputation. Sorry, I'm being critical of that, but...
Yeah, no, I mean, I think you're picking up on something really important, and, you know, it's one of these things where I violently agree with you. I don't disagree with you, I agree with you, and I was trying to get, there was one part of the talk where I was trying to say, it isn't, I can give the wrong impression, because you kind of focus so much on, you know, my strong belief is, if we can solve problems of being able to do recomputation in the boring sense and the archival, and yes, you can say all the things you've been saying, then everything else will be so much easier that we'll get all the benefits that you want. So I can go back and get, you know, Howlick and Elliott's code, whatever, and if I've read their paper, I'll just have so many benefits. So yes, there is a potential problem, and so I'm really pleased you raised it, because I do want to see that, but I think the thing to do is, if we can get it right for the basic thing of doing exactly the same thing, then we'll all be able to do different things better. That's the hope. That was...
It's stolen from the internet.
There's a URL
down there.
Yeah.
I have a very simple question, actually. You recompute, but you could also rebuild and recompute, right? So that you accept, okay, so your environment that you have is actually not only good enough to run, but also to rebuild the software that you want to run from source code.
Yes, the answer to that is yes, and I think I've seen this as really being part of the experiment. So if part of your experiment is to actually build the software to start with, then that's perfectly fine.
Do I have to give you my source code?
Not necessarily. So ideally, we would want the source code, because we want everything to be open and available to everybody. But if you don't want to, for whatever reason, or there's licensing issues like with Cplex, for example, then you don't have to. We're also happy to simply take binaries.
I think this is one. As I mentioned, there's a thing called the Science Code Manifesto, which is that is saying you should make your source open, and I am a believer in that, especially if it's government funded and there's a whole open access thing. But actually, I think it's an orthogonal thing, because I want your experiment to be recomputable, even if you're, in my belief, wrongly not making your code available. I still want the thing to be recomputable, and if that's a binary that we've got, so the answer is no, you don't have to, but you should.
So this is more of an implementation thing. If someone finds a bug in the code, then I guess there should be interface for authors so that they can update the code, because you run on a set of benchmarks and there was some problem with the format, and you give slightly different format and there was a simple bug. So I guess authors should have some access to update their code just to handle that kind of things. Because when we do experiments from other papers, you find that there are like slight bugs and the authors get to fix it. So I guess it would be nice if this can be integrated here.
Yes, but this is in a sense what we want to avoid. So once you have packaged up an experiment, and this is exactly what you ran, this is exactly what you're going to get. You can then create a new updated experiment which has the bug fixed, for example, but it's possible that you have bugs that affect your results, and we certainly want to capture that. Even if that only means that at some point later somebody is going to have a look at it and say, oh, actually, that order of magnitude improvement you got there, that was because you're running the wrong calculation or something, which, okay, would be a bit embarrassing, but that's certainly what we want to capture. So in particular, we don't want, it is not our intention to allow people to update the experiments as they go along so that it doesn't correspond anymore to what was run for the particular published paper.
So I think this can also serve as, although it's not your aim, but something you can get the source code and everything from. So for example, my code runs perfectly on the benchmark that I tried for the paper, but you provide another benchmark and there is a slight issue just with the format, and if the author could have updated that code, then it could just handle. Otherwise, I guess, what if I need the code, then I think Recomputation.org can serve as the website that I can also get the code from. I don't know if this can be one of the motive, but it would be interesting.
Okay, yeah. So I guess in general we would prefer it if you do want to make changes for whatever reason to the experiment, then it's a new version of the experiment, and you can certainly build on what you have previously had. But it doesn't, and you might even put a note on the description page saying this new experiment supersedes this old experiment, but the old one should certainly still be available. Of course, this only really applies if you're doing this, say, while you're developing your code, so that there's nothing published, you're basically just playing around with it, then it might make sense to not keep all the versions of all the experiments, because some of them there's not really any point in keeping all of it. But as soon as it's published somewhere, and you've made the experiment recomputable, that is something that should be kept forever, because it corresponds to the published version, and similarly, you don't change a published version of a paper after you've published it. You might publish a correction or an extended version or something like that, but that would be a different thing.
So I really like what you're doing, so thank you for the presentation. I think it was very useful. I'd like to actually add a couple of things or comments. I believe that it's a very valuable tool even in the development of a product for making a paper. Just for the ability to reproduce your result, your own result over time and avoid regressions. And it's very valuable to go back. I had the case even with my own code, new version of the compiler, what used to work 5 years ago, now it's syntax error. And you have to actually change because now the compiler is more compliant with the standard. And it would make my life so much easier if I could go back to my environment as it was 5 years ago every now and then. So I think that the value goes beyond just reproducing the experiment and sharing with others. It's even internally within your own group, that's a very valuable thing. I've learned about Vagrant, I didn't know that, I think it's very useful. One thing that would be nice, and to address that comment, is to really build into this versioning. So that if people want to start modifying, they can actually keep a history of whatever they're doing and you get the best of both worlds. But it's a very valuable exercise, and there is plenty to be had, especially reproducing experience from 10 years ago on current hardware. I suspect that there might be issues with parallel code, which is a separate comment, especially since on today's machine, we see machines that have dynamic voltage frequency. They change their behavior even on server class machine depending on the load, and you might see funny behaviors when you're testing into a classic environment that may not be visible when you are in a virtualized setting. So plenty of good reason to go ahead. Thank you.
Thank you. So just a quick comment on the different versions of the experiments. We haven't really started thinking about this, and I think that the main problem with that in our current approach is that you can't really version virtual machines. So of course you can just take the box, your 5 gigabyte file, your dump of the virtual machine, and put that into a source control system, but that won't really give you any meaningful differences between them. So I think that there might actually be some research in there, as in how do you, if you have 2 virtual machines and you know that they are slightly different, how do you automatically figure out that difference in a way that actually means something to a human?
So I just wanted to add something. So thanks very much for the comments. But also, again, on the versioning, and as Lars says, we haven't really thought about this very much. But one of the things, if we're able to automate things better, one of the things I would like to do in the longer run is, and it relates partly to Jimmy's question as well, which is, we've got this virtual machine and it's Ubuntu 12 or 13 or something, whatever it is, and it would be nice, we're not tempting to do this at the minute, to upgrade that to the next version. At some point the experiment might break, so you can't just, definitely, as Lars says, you would always have available the one that ran that day, but it would also be nice if you're lucky. There's an amazing video I saw, and this would be fantastic, we could do this kind of thing, where somebody took Doom, I think it was Doom, and installed it in MS-DOS, and then they just kept updating through to Windows 95, Windows 98, and it kept working. So it'd be wonderful if we could, you've got this experiment that ran 15 years ago, but it didn't depend, because it's a nice simple thing, maybe you could actually just keep updating it and run it in the latest Ubuntu as well.
This is going to sound like a really mean question. Have you just changed the problem from my code breaking when the C compiler updates to my code breaking when VirtualBox and Vagrant update?
I guess you could see it that way. I think it's between different versions of VirtualBox, for example, it's not quite as bad as between different versions of the C compiler, for example, because you know exactly what you're emulating. And in the worst case, so if VirtualBox went away, you would still have the disk image, which captures the operating system environment, all the binaries, all the instances, everything else you need to run. The only thing it doesn't capture is really the meta information about the machine, like how many CPUs did it have, how much memory did it have. But you could extract everything from that disk image and put it into a different virtual machine that you run using some other kind of provider that may use a different virtualization layer, and you should still be able to reproduce it.
I think at this stage, even in these few months we've been doing this happened. So there was a case where, I can't remember the exact details, but I think Lars sent me one of these boxes and it wouldn't run in a particular machine, and I Googled, and I possibly even had to backdate to an older version of VirtualBox, but maybe upgrade. So yeah, if the version of VirtualBox changes, your experiment might not work anymore, but one answer is keep around the old version of VirtualBox, which is actually quite important for sustainability. And the other one is, in the very long run, it wouldn't surprise me if we have to keep old machines, not the old machine like a Sun Spark 5, but the old machine that the right version of VirtualBox actually ran on, before. If we were doing Macs, we might have had to keep some PowerPC Macs lying around or whatever.
Hi, if I published a paper with some nice results and then nobody could reproduce them, doesn't that mean it wasn't a good idea?
Sorry, could you say that again?
So if I publish a paper on some new technique and I show some nice results, but they can't be reproduced, doesn't that mean it was a bad idea? It was a very specific technique. That
I think so one of the big things I said, and again Jimmy mentioned this as well, I'm not ashamed, I'm not embarrassed about the fact that yes, we are just doing your exact experiment in the first instance. And indeed the proper scientific reproducibility isn't what this project is about, because the proper scientific is somebody else implements it, uses a different technique or different brain, different programming language, and they show the thing works or not. And in your example, I think a really nice example of that as an analogy is something like cold fusion, where people weren't able to reproduce it in the proper scientific sense. I think it'd be fabulous to go back in time, if it was a computer science one, and the equivalent would be, I've got a polynomial algorithm for SAT on my computer, and let's grab it and study it, and maybe, if it's as interesting as cold fusion, somebody might discover what the flaw in the experiment was, or so you might actually go and you can examine the artifact. But yeah, I mean, if you're asking, you know, this isn't answering the question of how do we reproduce in the proper scientific sense. It's asking about how do we make sure that we can do what was done before.
But I mean, what's interesting about something like clause learning is that everybody finds it helpful on different computers and solvers. Why would they want to reproduce the original paper? And if it only worked there, it wasn't interesting.
It's funny you should say that. What a wonderful, I'm very glad, Steve. I'll come and you remind me later and I'll give you money. I gave a talk on Monday, for what it's worth, and I was talking about the exact way that watch literals moved in a SAT solver. And after the talk, and I said, I was completely surprised to discover this is not how Minisat does it, and blah, 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 blah. And Alan said, at the end of the talk, he said, that's how Chaff did it. But you can't get Chaff, right? So we can get Chaff binary, but not the source code by default. So if we had a virtual machine with the source code in it, then I could have gone and looked and said, oh yeah, that is how it did it. So that's a really nice example to me. Well, I would love to know exactly what the original paper with Chaff in it, what it did.
Thank you.